up, down, strain, charm, top, bottom. These have interesting names. And leptons, light particles such as the electron and the muon and perhaps even the tau that you may have heard of. And each of these particles has its sort of what I call corresponding neutral particle or the neutrino. Now, most of what we know in the universe, sort of the visible part, is sort of comprised really of this first generation that you see here, up, down, electron, and neutrino. But in addition to all of this, there is another important part of the Standard Model, and that is what comprises what we call these particles here. Now, you're aware of certain forces or interactions from maybe some of your work in high school as well as undergrad. And for example, there is the electromagnetic force, EM, which is carried or mediated by, we say, the particle called the photon. In addition, there is the strong force, which holds the nucleus together, which is mediated by the particle called the gluon. Then there is the weak force, which is responsible for beta decay and radioactivity, and that is mediated by these particles called the W and Z bosons. Now, this comes together, and before I go ahead and talk more about this, these are terms that I will be using sometimes, so I would want you to familiarize yourself with it. Fermions and bosons, all of the particles that I mentioned in my previous slide can be grouped into these broad categories. Fermions are particles such as the leptons and quarks that I talked about, which has this quantity that we call spin, intrinsic angular momentum equal to half. And on the other hand, the force carrier particles that we talked about are mostly what we call spin 1 particles. There is an exception, and I will come to that later. Now, different numbers of quarks, for example, 3 of these quarks could come together to form something we call a baryon, and in the end, they end up having spin half, 3 halves, 5 halves. And then you can have a quark, and it's what is called antiparticle. So every particle we say has an antiparticle that has similar properties, but different charge, opposite charge. So you can have a quark which has a certain charge, 2/3, 1/3, which can come together with this antiquark to form what's called a meson. Now, there's a fundamental difference between the properties of these fermions and bosons. And here is like a little cartoon analogy. You can think of as in 2 different kinds of, hotels, something called the fermion motel and the boson hotel. And if you think of a family of 4 coming in or more, and if they go ahead and they are of a nature where they don't like sharing rooms, but they want to be in their own individual room here, we say that they are fermions. That is, no 2 identical particles can occupy the same quantum state. On the other hand, you can have bosons who are very friendly. They don't mind sharing rooms, and all of them group or cluster together. And this is the basis of what you also probably might have heard of, the Pauli exclusion principle, that we are classifying these. Now, all of this worked beautifully for massless quanta, for the photon and the gluon, but then we started seeing issues that we couldn't really explain when we started looking at more massive particles, such as the W and Z bosons, or when we started to look at, for example, the masses of all of the leptons and quarks. We saw there was a huge range in their masses, from very, very tiny neutrinos and electrons, muons, and taus, to the gigantic top quark, which is shown here. This is all in scale of mass. So clearly, it indicated to us that the Standard Model, as we knew it at that time, was incomplete in the sense that there was something else that was needed. Some assembly was required to explain it, and this, or understand its features. And then this is what led to the idea of what's called the Higgs. And I will talk more about this in a second. And in principle, we need this for understanding how elementary particles get their mass. So you can think of the Standard Model as being something which worked very beautifully for a number of years. However, some things were incomplete. Some assembly was required. And another important piece, which you might have realized as you saw all of the forces that I had listed earlier, the electromagnetic, strong, weak, And I did not mention a fundamental force that we experience in our everyday lives. That is the force of gravity. Gravity was not or is not included in our current understanding of the standard model. And this is a big open question. Now, in order to understand the Higgs, it's useful sometimes to look at some analogies because it's a very, challenging theoretical concept, really. And for that, I'll invite you to take a look at this picture, which shows a parachute and a person attached to it, and they're, say, falling down through the air. And so the question is, if you were in this position, for example, what would you rather have, an unopened parachute or a fully opened parachute? And I think almost all of you will agree that what you really want is a fully open parachute because that's the safest way to come onto the ground. And here, what is happening is that there is interaction with the medium, which is air, and this lowers the speed of the drop, making it a safe sort of fall to the ground. In a similar way, you can think of the Higgs field as something that is permeating all of the space, and particles are interacting with it with different strengths. And depending on the interaction, if there is larger interaction with the medium, for example, that determines what kind of mass the particle has. I'll use another analogy to explain this because this is really an important, very, very important piece of what we work on. And this is a set of cartoons that were actually devised by David Miller from University College London in response to a request from the then Prime Minister of England, Margaret Thatcher, who wanted to understand what the Higgs was all about. So for that, you can think of that there is a room, and this room is really full of people, and these could be physicists at a conference or political party workers, as was the case there, and they're all talking to each other. Then what you have is a famous person who walks or enters the door. And as people realize that this famous person is there, they start questioning, oh, what's going on? Why is he here, etc. And imagine a situation where this famous person who's entered the room here is now trying to make his or her way to the other end of the room. Are they going to easily whiz through the room? No, they can't, because as they go through the room, groups of people cluster around them, trying to want to talk to them. Why are you here? What are you up to these days? And so the motion of this person is sort of slowed down as they make their way from one end of the room to the other. It's like they have acquired mass. It's like their heavy, massive objects move slowly. So their slowing down is sort of similar to their picking up mass. That is, the more they interact and talk with the groups of people around them, the more slowed down they have. And so this is this interaction with this field of this group of people that gives this person essentially their mass, and in our world, a particle, and how it interacts with this field around it is what gives us its mass. Now, let's imagine a scenario where a complete nobody, instead of this famous person, walked in. If this complete nobody is now entering the door and they want to get to the other end of the door, is anything going to happen? Are people going to want to talk to them, slow them down? No, that person is going to whiz through the room and is able to easily get to the other end of the room. So they have very minimal interaction. And as a result of that minimal interaction, it seems like they have almost no mass. They can go through in a very speedy manner. So again, this is the same principle. That is, you have a certain interaction with the field that exists, and depending on that interaction, you have masses that are being generated. So this idea actually was brought together by a number of people. You see them listed here, who essentially came up with this individually or in three different groups that were then all in the year 1964. So the basic idea was the same, though they were written from different perspectives. And three people, Guralnick, Kibble, Hagen, Higgs, Angler, and Brout, who came about with this idea of what has now come to be called the Higgs mechanism, resulting in three very important papers that laid the foundation of this work in 1964. So to summarize, Imagine that there is this field that permeates the entire universe. Every particle feels this field, but is affected in different amounts. And the more a particle interacts with this invisible field, the more mass it gets. So now I use this term invisible field. So with that, you're going to ask me, but if this field is invisible, how can we prove that it exists? Well, for that, the way we do about it is we take advantage of the fact that this theory predicts that associated with this field is a particle, the Higgs particle. And what we try to do in our experiment is actually to hunt or look for this Higgs particle. If we were to find this Higgs particle, and this was what we set out to do, then we could, in a way, verify that the Higgs mechanism was correct. So what we tried to do is to create the Higgs boson in our experiment, but we were faced with a challenge that the theories did not predict what the mass of the Higgs particle was to be. So we were really looking in a very, very wide range in as diverse ways as was possible. But that was not the only question. There were several other questions that we were set out to do with and work on with colliders. One of them is related to what I've already mentioned, that there is this very large mass hierarchy in the fermion sector. If you look at the masses of the quarks and the leptons, they are ranging from very little to very large, as in the top quark. And then, of course, you've heard me mention the number 3 a few times. I've said there are 3 quarks of 3 generations of quarks and leptons. But why 3? What is magical about 3? Why are they exactly 3 generations? Well, we don't know. There could be more. In fact, that's something we've been searching for and looking for as well. Then there is the question of how do we explain the matter-antimatter asymmetry in the universe? I don't know if some of you have watched this movie called Angels and Demons. It's an interesting movie. It's based at CERN. If you get the time, try to watch it. But its main actor is Tom Hanks. So I'm now using that as an analogy to say, let's imagine a scenario where there is Tom Hanks, but he would look very much like actually anti-Tom Hanks. That is his antiparticle, very much similar in properties, except for, as I've mentioned, the charge. And so Tom Hanks looks very much similar to anti-Tom Hanks. And now if they were to come together and to meet each other, well, they would completely annihilate. Now, at the start of the universe, the start of the Big Bang, we talked about, we know that matter and antimatter were all there, equal quantities. But what we see around us today, we are all matter. And we exist, and there is no naturally occurring antimatter that is inside. So where did all the antimatter go? And why are we left with this world that is so matter dominated? We don't actually know the answer to this question, though there are lots of ideas of trying to explain this. Then there is a question that if we look at our universe, only about 5% of it is what we called the visible, meaning we see it, we understand its interactions, and this is all that I've been talking about, all our quarks and leptons, etc. A large fraction of it is what we call dark, meaning we can't really see it, we can only infer its presence. For example, about 25% of it is what we call dark matter. That is, we don't know it, what it is, or what it is comprised of. We can only infer its presence through actually gravitational interactions. So what is responsible for dark matter? This is a big open question for us that we try to understand and address at Colliders. Are new particles the solution? And no, they're not particles like Darth Vader who are dark in our movies, but perhaps there could be connections, for example, between new completely exotic particles we haven't discovered, or perhaps the Higgs might have something to do with it and could lead to dark matter. These are all open questions that we are trying to answer. And then, of course, the question that I already mentioned to you earlier, the question of gravity. This is a mug that you can buy at CERN, which has the standard model Lagrangian in short on it. And a big important piece that's missing there is the fundamental force of gravity. What and where is gravity? Now, there are lots and lots of interesting ideas out there to try and explain what could be responsible or how we could answer some of these questions. For example, there are theories such as supersymmetry, which predicts that every standard model particle that we know of has a partner particle that is sort of what we call a supersymmetric particle. And so perhaps what we've seen is half of the overall total number of particles, because we've seen the standard model particles, and the supersymmetric particles are still left there for us to discover. Then there are the ideas of what are called extra dimensions. We know of the world as in, 3 + 1 standard dimensions, but maybe there are more dimensions. Maybe some of them are really small and curled up and compactified. And perhaps it's in one of these dimensions that gravity reigns and is strong and supreme, while in our dimensions that we are aware of, it is not so. So are there these extra dimensions? Are there particles that could be in these extra dimensions that we don't ordinarily see? Well, these are some of the questions that we are trying to answer. How do we do that? Well, we tried.
Do you want to take some questions?
Sure. I think this is a good time. I'll take some questions.
Okay, thank you. People is sending greetings to you from Miami, United States, Mexico, Peru, Guatemala. And people is asking that why fermions are fermions and why bosons are bosons.
These are excellent questions. And in fact, that's a fundamental question. Why are particles the way they are? Well, we fundamentally don't know why. We just know that these particles have these properties, and some particles end up having these particles, which means that they follow this kind of statistics that we call Fermi-Dirac statistics. And another set of particles which are actually seem to have properties which align well with what we call bosons. They follow what we know as Bose-Einstein statistics. But fundamentally, if a new particle were to be discovered, for example, whether it will be a fermion or a boson, I cannot really predict. So this came about as a result of the way the standard model was constructed by grouping particles and looking at symmetries and their interactions. But it's an excellent question.
Thank you. People is asking you, how does the G2 experiment results affect our understanding of physics phenomena and the standard model?
Could you just say what was the first question? What kind of experiments?
It's the experimental results.
Absolutely. So that's again an important question, because what I'm talking about, for example, I'm going to address in the next set of slides how exactly using experiments we discover those. But a lot of the times, for example, in 1964, a group of theorists came up with these predictions, which said, oh, maybe there is a Higgs boson. But until you can experimentally prove it, you don't know whether that's true or wrong. So what we've been trying to do at our experiments is actually hunt for these particles. So sometimes by our experimental results, we can validate theories and say that this theory was right. And sometimes we can look at our experimental results and say, these theories are completely incorrect and wrong. So the experimental results go hand in hand with the theoretical development to try and figure out what is correct and well-founded and what perhaps may not be.
Thank you very much. Miguel has a question. Could you say about yourself, Miguel?
Hello.
Hello.
Hello, doctor. It's a pleasure to hear your talk. Very interesting. You said that there are several potential answers for dark matter. What could be according? What do you think? What would you? Which potential answer would you choose? I mean, what do you think about the existence of dark matter?
An excellent question. So I would say on the basis of what we have seen in our data so far, some of what were commonly known ideas, that is dark matter is perhaps this weakly interacting massive particle, are less likely to be true. But maybe there is a more complicated answer to dark matter. And one of these is related to perhaps there being like, a completely a dark sector, which is in sort of parallel to our sort of sector. And then the Higgs boson can act as a portal to this dark sector. And maybe there are invisible decays of the Higgs that we will find that can prove this or disprove it. That's the one that I'm looking for in my experiment. And so I know there are other interesting ideas as well. New particles called axions, for example, which could also help explain. So it's a very rich field at the moment.
Thanks a lot for the answer. Shall we continue, Tulika?
Sure.
Yes.
So I think this was a good time because I've talked about sort of the theoretical motivation for why we do the experiment that I'm going to talk about next. And then this is because we are really trying to answer these questions, look for new physics, and then we kind of do this in two different ways. One is by looking very, very closely, so with a lot of precision using new techniques, and the other is just looking in new places by just putting in more and more energy to see what we can produce, or by just doing new measurements that we haven't done before. And so this takes me to the lab where I work, which is what we call the CERN lab, which is situated just outside Geneva in Switzerland. It's actually at the border of France and Switzerland. And it is here that we've been colliding beams of protons together at increasing energy over the years to see what happens as a result of those collisions. What are we able to produce? What new physics can be unearthed? And over the course, since the start of the Large Hadron Collider, as it's called, the LHC in 2010, we've had different collision energies as a result of the upgrades of the collider from 7 trillion electron volts to 8 trillion electron volts to the most recent run, which was called Run 2, where we had a collision energy of 13 trillion electron volts. And the run that is currently ongoing, we call it Run 3, which is at about 13.6. And so we're colliding literally protons, which are, which have about, in the case of Run 2, for example, 6.8 trillion electron volts with bunches of protons with 6.5 trillion electron volts. They come to collide at certain points, which are shown by these dots that you see here, at 4 distinct points, which is where we instrument the detectors. Now, I should point out that these protons are really traveling at close to the speed of light. And then this ring around is about 16.8 miles, so 27 kilometers, and they are going at about 11K times a second. And I've listed there the kind of speed you will have in miles per hour, so you can now compare it to a car or even a train speed to see how different it is. This is about 300 feet underground. We have about 1,200 magnets that are responsible for bending the beams and then making them collide, etc. And it's really cooled to about 1.9 Kelvin, so that's almost like being in outer space. And the energy of the beam is about 362 megajoules, which may not sound surprising, but it is surprising when you compare it to, for example, an equivalent number of TNT, which is about 90 kilograms of TNT. And what I personally found very scary because of my fondness for Swiss chocolate was 15 kilograms of chocolate. So there's a lot of energy in that beam. And therefore, when they come together and collide, you can really have some of the hottest reactions in our galaxy. And then you can look at what kind of temperatures these correspond to. It's a huge number, as you can see in centigrade. And around that point, we instrument our detectors such that we can observe what happens out of that collision. If you remember my cartoon at the very beginning with the balls colliding and what's happening out. And so here in the middle of the detector, this is the CMS detector, my experiment before it was closed up. And then you can get an idea of its scale by the size of the person who is standing here. So it is a rather massive detector. And it really acts like what I would call a gigapixel camera, which is just taking 1 billion pictures of interactions per second. And what we analyze are those interactions. There are actually 4 experiments situated around this ring, and there are 2 called ATLAS and CMS. A CMS compact muon solenoid experiment I work on. ATLAS and CMS are 2 general purpose experiments that do a wide variety of particle physics. There is another one called LHCb, which studies specifically the physics of B quarks, and then the ALICE experiment, which studies heavy ion collisions. The CMS detector, it took about 2,000 scientists and engineers more than 20 years to build. It's a rather complicated detector. It's about 15 meters wide and 21 meters long. It weighs about twice as much as the Eiffel Tower, or if it helps you, about 40 large airplanes. And there are different pieces to it, and I will talk briefly about how they're used to detect different particles. And what are these particles? So we've talked about photons, the light quanta, electrons, the lightest electrically charged lepton, muons, the heavier cousin of the electron, charged hadrons, which are composite particles, which are made of quarks, such as protons we've talked about. There are others, such as pions, kaons, and lots of them. There are composite neutral particles that are made of quarks, such as, for example, neutrons that you may know, as well as others. Now, how does a detector work? We actually have different types of detectors which use different technology, and then they try to harness important features of these particles. So, for example, at the very center, we have something called the tracking detector, which makes use of silicon technology, and a charged particle, when it goes through such a tracking detector, leaves hits, and we can sort of form a track. It's like footsteps on the snow, which allows us to figure out how somebody is walking. And so we can figure out the path a particle takes. In this case, I'll start with the muon that you will see goes through the tracker. So it leaves a track, and ultimately on the right-hand side are dedicated muon detectors where we can figure out properties of the muon, what kind of momentum it has, etc. Then there is the electron, which also is charged, so it will leave a track in the silicon tracker, and then it goes and it deposits an energy in a detector that we call the calorimeter, and this one is the electromagnetic calorimeter, which is specifically designed to collect energies from particles that interact electromagnetically, such as the electron and also the photon I'll come to in a second. There is a charged hadron, which will also leave a track in the tracking detector, and it deposits an energy in a dedicated detector we set up, which called the hadron calorimeter, which is designed specifically for hadrons. So now, using these different signatures, we can start to differentiate what may be a hadron from what is an electron with what is a muon, for example. Then now, I just talked about a charged hadron, but what about a neutral hadron? So a neutral hadron is different from a charged hadron because it will no longer leave a track in the tracking detector, which is going after charged particles. All it will do is leave a deposit, an energy deposit in the hadron calorimeter. So now we can distinguish it from the charged particle. And there's a photon, which is also neutral, so it's not going to leave a track in the tracking detector, but rather it will just deposit its energy in the electromagnetic calorimeter. So these signatures allow us to figure out what particles are being produced and how they're interacting with the detectors, helps us figure out their properties. And then there is the neutrino, the light neutral particle that actually does not interact in our detector at all. It sort of goes through it, and we can only sort of infer its presence by applying principles of physics, such as conservation of energy and momentum. We find something missing, and we attribute it to, for example, a potential neutrino. Now, all of this was the detectors, but there is a huge challenge associated with our experiments. And then this comes about that if you look at the rate of the interactions happening, that's about 10 to the power 9 per second. And these bunches of protons are colliding every 25 nanoseconds. So at a rate of about 40 million times a second, 40 megahertz. All of the money and the resources and the facilities that we have allow us to write out data and store it at the rate of only about 2000 hertz, so 200 events per second. So there is this huge gap between what is actually happening and what we can store. And it is complicated even further by the fact that the things we want to discover, they're actually quite rare. And so what we want to be able to do is extract this extremely rare discovery signal from the huge mess of data. And that means we have to have large-scale processing and data management. Here is this cartoon which shows you if all of the CDs are stacked with just the 1 year of LHC data, they are as high or a bit higher than where a plane flies, perhaps where an air balloon is, and higher than the tallest sort of mountain in the Geneva area. So it's like looking for a needle in a haystack when we are trying to find the interesting new physics signals, such as, for example, the Higgs boson that we were so interested in. Not just that, well, you don't have one proton interacting and colliding with another proton. You have bunches of proton colliding with bunches of protons. So you have more than one proton-proton interaction. You have several, and we call this overlap events or additional events or pileup. And when the LHC was designed, our detectors were designed, we were expecting about 25 such events. What we see already in our data is way more. And why this gets complicated is because in the end, we are need to figure out what is produced and where it came from. That is, which proton-proton interaction it came from. We don't want to find the end products from a different proton-proton interaction and assume it came for a different one, because that will lead to results that don't make sense. So you see here a cartoon or an event actually which shows about 78 vertices that were reconstructed where there was, for example, a proton-proton interaction. And we want to figure out all of what comes out of that. So it's quite challenging. As another example, I'll show you, so the Higgs particle that we say we're looking at to discover decays into 2 Z bosons, and each of the Z's decays into 2 muons. So now you have a final state which has 4 muons. And this was supposed to be a golden signature. We said, nice, clean way of identifying 4 muons, and we'll know we have the Higgs. When we first started looking at simulations of it, this is what we saw. And as you can see, this is just a mess. We can't figure out what is a muon here or where it's coming from. And then that is because you have to apply certain requirements that helps to eliminate and get rid of the pileup events that we talked about. So for example, if we require that we have tracks with a certain momentum, you can see it cleaning up. And now you have these 4 muons in addition that you can see very clearly in the picture. But the complication is that you have to find this from the mess. And this, and not the Higgs, is repeating every 25 nanoseconds because collisions are happening 25 nanoseconds. I can't simulate that, but this is to just give you an idea of the rate at which the events are happening. So the challenge is to really figure out where is that interesting event, where is that needle in the haystack, and the solution to this is what we call the trigger. In reality, this is not what it looks like, but rather it looks like this. This is an electronics board that I actually worked on as part of my PhD thesis. So I have very fond memories. So I always like to include a picture of it. But that was a while ago. So this is a modern day version of an electronics board that we are using in the CMS experiment to actually make some of these decisions regarding what's interesting and what we should keep, because it may be that needle in that haystack and what we should throw away. So this is then a description of how we do that. My experiment has, we call like a 2-level system for doing this, for selecting what are the interesting collisions to keep. So as I've mentioned, the collision rate is 40 megahertz. We have what we call custom electronic boards, things we have built and designed, and we have algorithms that run on that, which use information from the calorimeter and muon detectors. And they make certain very fast decision in the order of, microseconds, 3 microseconds, in fact, whether this event looks interesting. And if so, I keep it. If it's not, just get rid of it. And it's doing it in such a way that we are able to select about 100 kilohertz. so 100 kilo events per second. And what passes this, what we call the level 1 trigger, then goes on to a farm of what used to be commercial CPUs and now also graphics processing units or GPUs. And here you have C++ algorithms that run and try to make more precise decisions based on this input rate of 100 kilohertz. And then we write out about the order of a few kilohertz, 1 or 2 kilohertz. I should point out that the real hard limit is actually not the rate, that it is 1 kilohertz or 2 kilohertz, but rather the bandwidth. That means how large the events are and the rate combined, because that impacts how we transfer data from our online file system to actual storage at the end. So this is a brief summary of what our trigger system looks like. But the thing which kept people like me who worked on the trigger awake at night sometimes at the start of the LHC was, if you look at it, you have about 10 to the power 9 events per second coming into your first level trigger, out of which you're literally throwing away about 99.99% of them, keeping about 10 to the power 5 events per second, which then goes on into this farm of CPUs and GPUs that I mentioned, where at this high level trigger, again, you reject about 99.9%, keeping only about 1,000 or so or 2,000 events per second. So now these are the events that we store for analysis. Imagine you are doing an analysis and you have your analysis code and you're trying to find that supersymmetric particle or dark matter. And 6 months down the line, you find out that you have a bug in your code. Well, what do? You just go, fix your bug, undo your analysis, and there you go. You can rerun again. But what about the events that got thrown away at the level 1 NHLT? What if there was a bug there or something you forgot to anticipate? Well, those events are gone forever. There is just no way of undoing that. So an important question really for us is our sort of favorite new physics signal included in the very small fraction of selected events that we wrote out? And this was the challenge of the trigger that we tried to address in many different ways. But we were able to, and in fact, as a result of all of this work, the CERN experiments were actually in 2012 able to observe a particle that was consistent with the long-sought hit boson. And this was announced about almost 11 years ago, 4th of July, 2012, by both the ATLAS and CMS experiments, who presented their results and said that they observed a new particle which had a mass, and both of them independently found that this particle had a mass at around about 125 gigaelectron volts or GeV. This is one of those events, I call it like a groundbreaking event. You ask people in my field where they were that day on 4th of July, and they can probably tell you where they were because we all remember where we were when the announcement was made. Before I go further, I will talk briefly about a few different things that I will mention. And one of these is what we call Feynman diagrams, because these are pictorial representations of different processes that lead to the production of the different particles that, such as the Higgs boson that I will
Tulika,
talk about.
do you want
Yes.
to take more questions?
Yeah, happy to.
Thank you. People is asking, what is a neutrino?
Very good question. So a neutrino is a particle which was found to have very interesting properties in the sense that it was neutral. And then it turns out that each of these particles, such as the electron, muon, and tau, have a neutrino that's associated with it. And when the particle was discovered, not much was known about it, except that, for example, it was neutral, and there were different types of neutrinos, such as the electron neutrino, the muon neutrino, and the tau neutrino. We thought that it was massless. It had no mass, which turned out some years ago that actually was not the case. And in fact, neutrinos have a tiny, tiny mass. But for example, what's the antiparticle of the neutrino, and what can explain the mass of the neutrino? These are still open questions. And what becomes challenging is that the neutrino, because it's neutral and is so less massive, it has minimal interaction with generic detectors like my detector, which is why we can't detect it. However, there are some very dedicated experiments, such as, for example, an experiment that's being constructed in the US at Fermilab at Dune, which is really trying to design dedicated detectors which will actually try to measure better the properties of the neutrinos and understand them better. And perhaps that will explain a lot of these open questions.
Thank you. Thanks for your answer. Translate from Spanish the next question. What are the new technologies that people is using in the accelerators?
A very good question. And here there is a whole range. So I'm not an accelerator expert, I have to firstly admit, but there is a lot of development, for example, in magnet technology. And what we want to be doing is, if we want to be getting to the next generation colliders, for example, which will collide particles at higher and higher energies, we need to be designing, superconducting magnets with technology that is able to allow us to actually get to those high energies. So there is a lot of development right now ongoing in that area. There are also completely different accelerator technologies, for example, those using plasmas and Wakefield accelerators, they're called, which are very different from the kind of accelerator, let's say, which is used at the LHC. So there is, it's a very active field of research with people thinking about what future accelerators should look like.
Thanks for your answer. Miguel, go ahead, please, with your question.
Thank you, Julian. Dr. Tulika, Higgs boson has been called the divine particle. It was predicted theoretically and discovered experimentally, and for that reason, he was awarded the Nobel Prize. But what would happen? What would be the implications in the physical world if this particle had not been, let's suppose it does not exist? So what would be the implications in physics, and why, maybe could you tell us why they call it the divine particle? Thank you.
So I guess that's a very good question. So this came about by a book which Leon Lederman, the name
Yes.
of the series, wrote, which was called the God particle, and there are lots of reasons people say for why it became called that. But it is, in my view, it's the particle that people were really hunting for over 50 years, because it was predicted in the 60s, but it was really fundamental to our understanding of what we call electroweak symmetry breaking, or how fundamental particles get their mass. Without the Higgs, if we had not discovered the Higgs, this is extremely dissatisfying, because you just cannot answer some very, very fundamental questions. We still don't know. We think that the Higgs that, that I've just mentioned, we've discovered at the LHC, is the Higgs that was predicted by Peter Higgs and others. But there are still possibilities that there may be, for example, additional Higgs bosons. And some of these is really critical for our understanding if the Higgs is the answer in some way or the other to some of our open other questions. And so I would say that if the Higgs had not been discovered, we would be designing and building different experiments to hunt for it, because it would tell us that maybe something is really weird about it. And maybe we can't find it because it's decaying in weird ways, which we can't detect in our detectors. So it was I would say people sometimes call it, the holy grail of particle physics in the most important particle to discover.
Thank you. Thank you very much.
Thanks for your answer. Shall we continue?
Sure.
Thank you.
All right. So just a few words about things I will be using, such as, Feynman diagrams, something we call cross-section, which is a probability that a particular interaction occurs. There are units called Burns, which has history coming back from how it was used in the fission era to describe the size of a, uranium nucleus. It's usually in centimeter square or area square. And all of this comes together because you combine the cross-section, this quantity sigma, with the luminosity, which is a function of the machine and a measure of the number of collisions that can be produced in detector per centimeter square and per second, giving us this event rate, this quantity n. Sometimes you will hear the term what's called integrated luminosity, so many inverse femtobonds, etc., which is really referring to how large our data set is, because it is giving us an idea of the number of events we've collected. Now, where the Higgs was concerned, it was predicted that, in a way, if this was to be existing, there would be different production modes. And so these are different Feynman diagrams, which correspond to different ways in which the Higgs can be produced. I don't have time to go into each of these, but I just want to give you an idea of how detailed our searches are, because we understand that it may be produced in all of these different ways. Some of them, such as the one on the top, which is called gluon-gluon fusion, has the highest sort of rate. So clearly we want to look for that, but we also want to look for the others production modes, because maybe they have better signal over background and maybe better in some cases to look for. We also look for what are called different ways in which the Higgs decays. I've already mentioned, for example, Higgs decaying to 2 Z bosons. It can also decay into 2 Ws, or to bottom quarks, or to taus, or to photons. And depending on the mass of the Higgs, some of these possibilities have a larger rate of happening, for example, in comparison to others. But as I had mentioned before, we didn't know what the mass of the Higgs was going to be, so we had to be prepared to search for the Higgs in all of these different ways. Now, how is it that actually we do this? Well, particles interact. We're talking about collisions that happen. And in most of these collisions, which are happening at, say, the main interaction point, what is produced, these particles decay very close to it. So we measure the event vertex where the interaction is happening using tracking information. Now, as I'd shown before, there can be a lot of sort of what I call background things, pile up, the low momentum things. We want to be able to reject that. And then we can, for example, use information from our tracking detectors. How a charged particle bends in a tracking detector tells us what its momentum is. How it bends this way or the other way tells us about its charge. So we use that information. We use the information of energy that's measured in the calorimeters, and then we plug it into what you may have learned in relativity, etc., to get, if you have E and if you have P, you can get to what the mass is, or in other words, start to identify particles. And so if you can, for example, look for a decay where the Z decays into an electron and positron, by figuring out the electron and positron, you can get the invariant mass of its parent particle. And if you find that its invariant mass is 91 GeV, which is the mass of the Z boson, you've got it. So in the case for the Higgs, this is the case on the top right, you see a Higgs which decays into 2 Zs. One of the Z's decays into mu plus mu minus, and the other Z decays into an E plus E minus. So we try to reconstruct each of these Z bosons and then see if these 2 Z's come from the same point, the same parent particle, and if so, what's the invariant mass of that? And we get that is about 127 GeV in this case. So we say, and we theorize, there is a particle which has a mass of about 126, 27 GeV that has characteristics or signature similar to a Higgs to ZZ decay. But of course, one of these is not going to make a discovery, but what we saw in that first data set that we collected back in run 1 was, and this is a plot on the right, which shows in blue the different background processes. In black points with the bars are the data points. And around here, about 125 GeV, you see the data points match up with a simulation for what 125 GeV Higgs would look like. We basically saw an excess of events at around 125 GeV, which was above and beyond the blue background. And we found that this could be consistent with the Higgs. However, if so, the Higgs just does not only decay into Z's, it also decays into photons, it also decays into W's. So we should be looking for those. So indeed we did. So we tried to, on the left-hand side, you see where the Higgs decays into 2 photons. So we tried to find the invariant mass of 2 photons. In the falling distribution is the background prediction, and around 125 GeV, we see a bit of an excess here. And the interesting thing is, this is exactly at the same point as the one on the right. So 2 different decay modes, both of them showing a parent particle at 125 GeV, in one case decaying into 2 photons, and in the other case decaying into 2 Z bosons. So that gave us confidence that we have something, because it's showing up in many different ways, not just one, and there are lots of events which are starting to show. And we got further confidence when we, as in CMS, produced this result, and our competing experiment Atlas produced exactly a very similar result with the particle exactly at around the same mass, which gave the whole world the confidence that we had discovered the Higgs. So I can go on in case there are any questions, but otherwise I will talk about what we've been doing since we discovered the Higgs. I'll pause in case there are any questions.
Thank you. Thank you very much for your talk. Yes, there are some questions. For instance, how do they reconstruct interesting events?
Okay, so well, I think I'll go back to this picture. So a priori, we do not know if it's interesting, right? We try to reconstruct whatever we can reconstruct. Firstly, we have constraints that we can't write out all of our data. So our first choices are made in the trigger, where we say, if I have, an electron and a positron above a certain momentum, it's potentially interesting and I'm going to keep that event. Later on, when we are doing a more detailed analysis, we try to see, what we find is really from our detectors information of there is some particle that has deposited energy in the calorimeter, and that has left tracks in the tracker. We don't know what that is. So we're kind of like, you can almost think of like detectives, solving a murder mystery. A murder has happened, and who is the murderer? What we have are clues in our detector, tracks and hits, and we try to pull all of these different pieces together. And if we start to see that there is a trend, that there is a particle that left a track in the tracking detector and deposited energy in the calorimeter, perhaps that's an electron. Now let me see if I can look at how much the charge track has bent, because I get the momentum. And now if the momentum is substantially high, that means it's potentially coming from some high massive particle. If it's a low momentum, then it's probably background and pileup. So by putting in these requirements, firstly identifying objects such as electrons, muons, jets, which are hadrons in our detector, and then looking for typically, not always, high momentum thresholds. So large momentum, large amounts of energy, we start to think, okay, this is interesting. And we have C++ algorithms that then combine information from all of the detectors to come up with the full picture.
Thank you. Thank you for your answer. I'm going to read directly from the chat the next question. Did you think the graviton is going to be found in the LHC?
I hope so. So the graviton is indeed one of these hypothetical particles. So as I've mentioned, gravity is the fact that we cannot explain gravity in the standard model is very, very unsatisfying. So there are theories out there which predict that there is this particle called the graviton that exists. And if it were to exist, there are certain ways in which it would decay and has certain properties. And in fact, some of my own students are doing searches using LHC data, trying to look for those specific signatures by which we may be able to identify a graviton if it were to exist.
Thank you. Thanks for your answer. Another question is it possible to explain the origin of electric charge in the same way as mass?
Ooh, that's an excellent question. I have to say, I don't think I know the answer to this question, and I don't know if maybe some others, maybe, but I'd have to ask my theorist friends. But no, electric charge is again one of those fundamental properties. The idea of mass comes out of what we call electroweak symmetry breaking, which would be probably a whole seminar by itself. So they're distinct in that sense. Charge is a fundamental property. We hope we understand it better one day.
Thanks for your answer. Thanks also for giving this interesting seminar. Unfortunately, we are out of time, but we appreciate your time and knowledge. Do you want to say some closing remarks for your public? Sure.
I can say is maybe I will just go to my one slide, which I think, as I said, I focused on the Higgs discovery and how we've enabled it using our detectors and everything. However, even though we've discovered the Higgs, there is a lot of open questions about whether it's elementary, whether it's composite, how does it couple to other particles? And so all of the work that we are doing right now is really trying to understand, are there exotic Higgs decays, additional Higgs boson? Does the Higgs boson, and will it be able to explain dark matter? And so I think we're at a very exciting time with lots and lots of data that is available, and a whole lot more. About 95% of the LHC data is still to come. And with that, over the course of the next 10, 15 years, we really hope to be able to get to the bottom of these questions and help answer some of the fundamental questions facing us today.
Thank you. Thank you very much for your interesting talk. All of us enjoyed it. And have a good evening.
Thank you very much for your comments and questions. I enjoyed answering them.